Me again, folks, and today another short one, hopefully, talking about calculating the axis on an ECG. Aims of this brief talk today are for you to be able to understand what we mean by the QRS axis and for you to be able to qualitatively calculate the QRS axis on a ECG. There is a more advanced method of how to quantitatively calculate this, which in the future I may try to put together another teaching session on. But for your purposes now, especially for phase 2, this qualitative calculation should be more than enough. Often you'll just hear people refer to the axis of an ECG. Unless otherwise specified, what they are almost certainly referring to is the QRS axis of the ECG. The QRS axis simply tells us the average direction of electrical activity in the heart during ventricular depolarization. This average direction of electrical activity of ventricular depolarization is simply measured against the hexaxial system of the limb lead, to that first half of the ECG. You will find that there is some degree of variance looking at different sources or textbooks as to what is counted as a normal axis. I personally count it as between -30 and +90. Left axis deviation would therefore be from -30 to -90, and a right axis deviation from +90 to +180. You could then call anything between the +180 and -90 an extreme axis. Hopefully it seems fairly obvious to you that in health, the overall average ventricular depolarization would occur somewhere in this normal axis range shown here in green. If the average direction of ventricular depolarization shifted up to the left towards this blue area, hopefully you appreciate that that probably indicates the potential for some pathology or abnormality there. Equally, if the overall activity of the ventricle shifted round to the right, then that would also potentially indicate something outside of a normal ventricular depolarization pattern. This is a brief aside looking at how we might class QRS complexes as either predominantly positive, predominantly negative, or equiphasic, meaning that the complex shows equal parts positivity and negativity. Going back to our hexaxial system, both leads 1 and AVF read in the direction in which we would expect normal ventricular depolarization to occur. We can use this knowledge, therefore, to look at the QRS complexes in both leads 1 and AVF. If the complexes are predominantly positive in both of these leads, we therefore know that the patient has a normal QRS axis. AVF, however, sits right on the edge of that sort of normal access range. Therefore, if we find that our QRS complex is predominantly positive in 1 but negative in AVF, we therefore can go to looking at lead 2 to see what the complex in lead 2 is doing. If our complexes in both leads 1 and 2 are positive, we therefore know that we're still sitting within that normal access range, although it's probably shifted slightly further around to the left than in a ECG where you had a positive complex in both 1 and AVF. However, in an example where you had a predominantly negative QRS complex in both AVF and 2, but a positive complex in 1, you can reason that that QRS axis has shifted round to the left outside of that normal range. If you have a negative complex in lead 1 and a positive complex in lead AVF, then that overall direction of ventricular depolarization has shifted round to the right outside of that normal axis range. So that would be a right axis deviation. An ECG in which you had negative complexes in both 1 and AVF could be considered to be an extreme axis. You can put all of this together into a table which gives you the QRS axis of an ECG by examining leads 1 and leads AVF, and if required, leads 2, looking at whether the complexes are predominantly positive or predominantly negative in those leads. In reality, however, most medical students simply learn this by examining leads 1 and 2 and learning that if you go up in 1 and up in 2, it's a normal axis. If you go up in 1 and down in 2, it's a left axis. And if you go down in 1 and up in 2, it's a right axis. This is an oversimplified version, really, but in most scenarios, for your purposes, it may serve you well enough. So why do we care? Deviation of the QRS axis from the normal can give us some insight into pathologies such as chamber enlargements, abnormalities within the conduction system of the heart, sometimes myocardial infarction, and sometimes we can work out the origin of some arrhythmias. It is, however, important to be aware that there are some non-pathological factors that affect the QRS axis. At birth, we all tend to be right axis, and then as life progresses, this axis shifts more towards the left. Tall, thin people are more likely to have an axis which is close to a rightward direction, so close to a positive 90, whereas short, obese people are more likely to have a QRS axis which shifts up towards the left, so closer to 0 degrees on the hexagonal system. A left axis can be part of a number of different pathologies. We will talk about some of these in future talks, such as left bundle branch blocks. Hopefully a few of them should seem fairly obvious to you, like a left ventricular hypertrophy. If you have more mass in your heart muscle on the left hand side, your overall direction of electrical depolarization should intuitively switch up towards that left side. In future talks, we should also talk about the clinical relevance of a right axis deviation, but for now, here's a list of some of the pathologies that can have a right axis deviation as part of them. So that's it for now. Hopefully now you have a greater understanding of what we mean by the QRS axis and would be able to qualitatively work out on an ECG what the QRS axis was.